So in this module, one video, we'll be talking about tracking population health. Our learning objectives are to distinguish between various types of measures we use in epidemiology to assess population health, specifically counts, proportions, and rates. We'll define incidence and prevalence and talk about how they relate to one another. And finally, at the end of this module, you should be able to discuss how different measures relating to screening tests, specifically sensitivity, specificity, and positive and negative predictive values, are used in practice. So let's start with the basic types of measures. The first is a count, and so this is simply the number of events or cases of a disease. It's the simplest measure that we have quantitatively, but the downside is we don't have a denominator for it, so it's not always clear what it means. So you might have 20 cases of diabetes, but you can't really interpret that unless you know what the underlying population or the source of those cases is. Another basic types of measure that we use in epidemiology is a ratio, so where we divide one quantity by another, and that's incorporating a denominator. So an advantage over a count is having that denominator information. And so there are various kinds of ratios you will see in epidemiology. One is a proportion where we just have the count divided by the group size, so the people in the numerator also appear in the denominator. We can also calculate that as a percentage, so just multiply that proportion by 100. And then we have rates, and so rates are very commonly used. They're a nice way to compare across populations, and a rate is a ratio expressed as a function of time. So here's a basic calculation formula for a rate. We have the number of events in a population during a specific period of time, and we divide that number of events by the number of people in the population who are at risk for the event during that same time period. And you may remember from earlier videos in this module, we talked about what at-risk means in epidemiology. And again, that's just having a non-zero chance of experiencing the event or the outcome. So people who are at risk are people who are capable of becoming one of those cases. They can potentially move from that denominator into the numerator. And the example I think we used before is if we were looking at uterine cancer, we would want to only include women in our denominator. Only women are at risk, and specifically only women who still have a uterus. So we would ideally exclude all women who had a hysterectomy as well. So probably the most common type of rate that you will see is a mortality rate. And so that's just the number of deaths in a population during a specified time period divided by the number of people in that population. So everyone who is alive is at risk of dying. Therefore, we can just use the entire population when calculating mortality rate. This might also be called an overall mortality rate or a crude mortality rate if we're using everybody in the population. And we'll talk in a future module about how we might want to adjust rates, so accounting for differences in age structures, for example, over time or across different populations. But this is a basic mortality rate. You might see an infant mortality rate where we're looking at death within the first 12 months of life. So various permutations of this type of rate calculation within mortality and beyond. So here is an example with numbers in it. So if we wanted to calculate the mortality rate in the US in 2007, we could go to vital statistics records, which we'll be talking more about in the future, and get the number of deaths. So it's just over 2.4 million. And then we would use the census as our source of denominator information. So we try to use the midpoint population size for our denominator if we can. So in this case, we'd want the population of the US on July 1st, 2007. And so that was over 301 million people. And so if we just divide those two, we come up with our rate of 803.6 deaths per 100,000 population per year. And in this example, the year was 2007. So the nice thing before I move on about rates is that they account for the population size as a function of their measure. So even if you're comparing the mortality, for example, in a county in Georgia to the country of Georgia, you can still compare those rates because even though there are very different population sizes, different numbers of people living in a county in Georgia versus the country of Georgia, you would be comparing on a per 100,000 people rate. And so if you see differences between those two mortality rates, it's not because of differences in the population size, it's some other characteristics. So we'll talk about that more again later, but I just want to highlight the point that rates already account for the number of people who are in the population, and so you can compare rates across different groups regardless of their size. Okay, so let's move on to talking about two of the most common types of categories of measures that we use in epidemiology to talk about the burden of disease in a population, and those are prevalence and incidence. So prevalence is just a proportion or a percentage, and it's expressing the number of people who have a particular condition at a given point in time out of that full population. So existing cases of disease. Incidence, however, is a rate, so we need to incorporate that time aspect into our measures of incidence because it's the number of new cases that a population experiences, and so we need that time frame. We need to know over what period of time are we talking about. So this is the figure from your textbook, chapter 3, that shows the relationship between incidence and prevalence. And so this pictures it as kind of a faucet. So incidents are those new cases coming in, and we have this bowl or sink under the faucet where we already have some water in there because there are already people living with the disease. So that's the prevalent cases. And so as you can see from this example, there's also another kind of spout coming out from the bucket under the sink. So people can leave that prevalent population either through death, or in some cases, if it's a condition that you can recover from, they might recover and go back into the at-risk pool, or just leave the at-risk pool altogether. So you can see here that if prevalence is really high, that sink would be more full, but if incidence is high, it would be filling up faster. So basically, incidence and prevalence are related to one another, typically as a function of duration of disease. So how long people stay in that prevalent condition. So here's another, this is how I think of it, which is the same idea, but a little bit more complicated maybe. So first, starting with that population at risk, those are the green dots there at the left-hand top of the screen. So among those people who are at risk of the disease, some number of them, those red dots, will develop the disease in a given time period. Let's say this is a year. So those are the incident cases of diseases for that year. And so they get added into this larger bucket where people who are already living with the disease, those prevalent cases, are already in there. And again, they can leave either through dying or through recovery. So mortality rates and recovery rates also influence the prevalence of disease along with incidence. So prevalence and incidence, as I said before, prevalence is approximately or proportionally equal to incidence times duration of disease. Another aspect, and this doesn't really relate directly to measuring disease itself, but we talked in an earlier video about secondary prevention, so the 3 levels of prevention. And secondary prevention is detecting disease early. And so in order to do that, we need to have screening tests for disease that are effective, that work well. And so the way we measure whether or not a screening test is worthwhile, if it does its job, is by using sensitivity and specificity. So this table here shows the setup that we would use, where we have the true status of people across the column headings, so people who have the disease we're interested in, and people who don't have the disease. And then we have our test results in the 2 rows, so testing positive and testing negative for disease. And so people fall into one of these 4 cells. We have our true positives, so people with disease who test positive on our screening test, and that box is typically labeled A. We have on the diagonal there people without disease who test negative, and so those are the true negatives, and that's D. So of course we want to maximize those 2 cells, but we have the off-diagonal cells of our false positives, people who don't truly have disease but test positive, and our false negatives are people who do have disease but test negative on our screening test. So sensitivity is the probability of detecting disease given that someone has it. So to calculate that, we divide A over A plus C. So that's our true positives out of our true positives plus false negatives. So true positives out of all of the people who have disease. And then specificity is the probability of not having disease or testing negative given that you don't have disease. So that is our true negatives out of everyone without disease. So D over D plus B. And we typically multiply those by 100 to get a percentage. So for sensitivity and specificity, the higher the number, the better for a screening test. So ideally, we typically want to have something in the 80 to 90% range at least to consider it as an effective screening tool. And so the text of what I just said is on this slide here. There are two other measures in addition to sensitivity and specificity that we want to calculate, and these help us determine whether or not it's useful or worthwhile to implement a screening test or a screening program within a particular community. So these values are the positive predictive value and the negative predictive value. And so they're the ability of the test to predict the presence or absence of disease, and they're specific to our population. So they are sensitive, or they're influenced by sensitivity and specificity, but they also incorporate the prevalence of disease in the population. So as we have higher and higher prevalence of the disease that we're screening for, our positive predictive value actually goes up. But as that prevalence increases, our negative predictive value goes down. So positive predictive value is just the proportion of people who test positive and truly have disease. So basically the likelihood that you really have disease if you test positive on the screening test. And the negative predictive value is the proportion who test negative and truly don't have it. So how likely is it that if you get a negative result, you really don't have the disease of interest? So this is another textbook figure here, and it demonstrates that as the prevalence of disease decreases, so that's the very top row there, we go from a 50% of the population having disease to 10% and 1% with the same screening test. So you can see across the bottom there that sensitivity is 80% and specificity is 90% across all three scenarios. So those measures relate specifically to the test itself, so they don't change in different populations. Those are fixed attributes of the screening test itself. But below that, you can see that the positive predictive value and negative predictive values change pretty substantially across these three scenarios. So in the case where we have a high prevalence of disease, where half of the population that we're screening actually has disease, positive predictive value is almost 90%. So if you got a positive test, there's a 90% chance or 89% chance that you really have disease. And negative predictive value is also pretty high. So 82% of people who test negative on the screening test really do not have disease. But as the disease prevalence decreases, so does our positive predictive value. So we see that in a population where only 1% of people have the disease we're screening for, there would only be a 7% chance that someone who tests positive is truly positive. So this is part of the reason that we don't typically screen the entire population in low risk groups, because we get very high negative predictive value, but we already know that most people don't have disease just based on the prevalence, so it's not terribly useful, and only 7% of people would be truly identified as positive in a very low prevalence setting like this. So it's not a good use of resources, and there's also the potential that, anytime someone screens positive for something, we only want to screen for diseases that can be treated, and so that person would then go through follow-up, incur additional costs, but also additional risks associated with future treatments. And if there's a low chance that they actually have the disease, even if they screen positive, we just don't want to put them through that cascade of events, and we don't want to pay for it as a health system if there's no benefit. So these are some considerations, some things to think about before implementing a screening program. So first, we want to know that the test is good, that it is a good indicator of the presence of disease. So we want high sensitivity and specificity values. But we also want to think about the prevalence of disease in our population. So again, we want that to be high enough so that we get a high positive predictive value when we administer the screening test. But beyond those basic measures, we also want to think about the test itself. Is it difficult to to administer, to do? Is it expensive? Is it safe? And are people going to be interested in using it? Is it acceptable to people in the population? We also want to think about disease severity. So even if we can detect a disease or condition, if it's likely to resolve on its own, or if it doesn't have serious implications, it may not be worth screening for. And finally, as I said before, we certainly don't want to screen for things that we can't do anything about. So you want to make sure that there's a treatment possible, but that it's also accessible to people, that people who screen positive are likely to be able to get the follow-up they need and the treatment that they need to address the health issue. And again, we want to make sure that treatment is acceptable within the population as well. So in summary, there are different ways to measure the burden of disease in population. We tend to use rates in epidemiology because that accounts for differences in population size, and it also gives us information specific to a time period so we can look at trends over time. We also frequently use incidence and prevalence when we talk about the burden of disease. So incidence is new cases, prevalence is existing cases, and both of those are important to think about when we're planning for health issues. They can help us understand what proportion, what the magnitude of a particular health issue is in the population. When we think about screening tests, so trying to identify people who have disease and get them into treatment, we want to think about sensitivity and specificity as measures of the test itself. But then we also want to calculate positive and negative predictive values so we can decide whether or not it's actually going to be useful to implement a screening program in our particular community. So that's the end of this module.